Good morning, everyone, and welcome to this workshop. Before I explain the origin of this title, Comets, Harbingers of Doom or Agents of Life, just an overview of what we're going to be doing. As with so many of the workshops, we are going to be taking specific ideas from a story that we can tell that excites students, but trying to use those to teach the concepts that we need to teach for primary school, middle school, high school, all the way up to university level. Some of these activities you will have seen before, some of these activities will be for the first time, but I'd be delighted to hear the sorts of discussions you are having, that whenever we are doing the activities, think of how it focuses with your students and how you can use those. Because I will come up with some ideas, but you will already, and I've already in this conference, picked up so many ideas I had never thought of that I could use these activities for. Now, we're going to be trying to understand the role of comets. How have they influenced life on Earth? Have they been instrumental in helping life get started on Earth? And have they changed the way that life has evolved on Earth? We'll be looking at the way we are exploring comets with spacecraft, in which the European Space Agency has had a real lead. But before we do any of that, we all know the answer to this question, even though our students very often are surprised. Space is only 100 kilometers away. That is closer to where we are now than London is. But it is 100 kilometers vertically upwards. And if we want to get to space, we have to fight against the force of gravity that has controlled the way that life has evolved on Earth for billions of years. If we want to stay in space, we are dealing with an environment that is tougher than any environment we have on the Earth's surface. So when we see a view like this, which was from the Space Shuttle mission STS-114, in 2005. This is the underside of the space shuttle. It's a very unusual perspective. This sort of view, in which we have a beautiful perspective on how thin our biosphere is, this sort of view really shows our students how thin the atmosphere is, how close space is, and we must never forget that since 1961, only 500 people have ever had this sort of view, and 19 of those have died in the process. Going into space, be it unmanned or be it manned, is still pushing science and engineering to the very limits. We must never forget that. Now, my first demonstration is something I feel really passionately about. It's the way that we use mathematics in science. Now, if we look at this photograph here, this was taken by the Galileo spacecraft going to Jupiter. It was a perspective photograph with the Earth and the Moon, so the Moon was in front of the Earth. Now here we have the sort of image that our students see in textbooks from primary school all the way to university level. We have lots of angles, we have lots of inclinations, but what I would like you to do is look at the data about the Earth, the Moon, and the distance between them. Looking at this image, what is very wrong with that image? It's the whole idea of scale. And even those of us who love mathematics, when we see the words not to scale, we can sometimes be misled because we are a very visual species as human beings. So, simple demonstration about the language of mathematics. I need a volunteer, please. Who is going to be my volunteer? Thank you very much, sir. So, can we give him a round of applause, please, for being the first volunteer? Okay. Now, what I have here is a globe, and if I look at the Earth-Moon distance, from my knowledge of pi times diameter, circumference of a circle, blah, 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 the Earth-Moon distance, on average, is roughly speaking 10 times the distance around the Earth at the equator on a circumference. It's 9.5 and it goes between 9 and 11, but 10 is an easy number to remember. Because what I have done is I have wrapped a piece of string around here 10 times. Very simple to remember. will work with any globe. Now, before we start this demonstration, when we look at the moon and the Earth, and we look at the maths, the moon is about a quarter of the diameter of the Earth. So the moon is about the size of Australia. Pretend that this is round. It's about the size of Australia. When you see the moon in the night sky next time, look up, put Australia there, you will get a perspective of the size of the Earth-Moon system. I'd like you to hold your moon. Can you hold it up, please, so we can all see? And I'd like you to take the end of the string. Now, carefully, because we've got a screen behind you, so you might need to look over your shoulder. Slowly going to ask you to move backwards, but every now and then stop. Stop! Okay, this is the picture that our students have. And we are misled. There is a lot of string that's left. So let's keep going. And I am hoping that if you have not seen this demonstration before, you will be surprised at just how far away the moon really is. Now, we're going to lose him out of the lab there. Okay, where are you? Over here, shout louder. Okay, so if you can't see him, you can certainly hear him. When our students see this, they're absolutely amazed, because the language of mathematics is telling us a story much more powerful sometimes than we can imagine. But it's even more amazing because space, 100 kilometers, is only 2 millimeters from here. The International Space Station that Krista was talking about, 380 kilometers, that's the width of my finger. The moon is 1,000 times further away than the altitude of the space station, 800 times further away than the orbit of the Hubble Space Telescope. So there are all sorts of scale activities that we can use with our students from primary level, again, to pre-university level. Space has so many of those. Okay, thank you very much, and can we have a final round of applause, because he is back in from the far depths of the high bay. Okay, thank you very much.
Thank you.
Now, just some other examples of scaling activities that we can do. We don't just need to think about space. We could drive to the moon, drive to the sun. Students work this out. When they're driving to the sun, it takes them 150 years. They're doing the calculations. They think they've gone wrong. And they start to understand so much better the scaling and the power of mathematics and powers of 10. But this is a lovely one from chemistry. If I look at the size of the atom, and I 10 to the minus 10 meters, and I represent an atom by a marble this big, we calculate how many atoms would fit across my fingernail. The answer is 100 million. And if each of those marbles is this big, we get the students to calculate how big would my fingernail be. And some of them say it'll be the size of this room or the size of Noordwjik. When they do the calculations, it's actually the size of France. If your atoms in your fingernail were this big, your fingernail would be the size of a country. So again, so many ideas for scaling that we can use. Now, since 1957, we have sent hundreds of human beings into space, thousands of satellites, and they have changed our understanding of the world. We have global telecommunications. We have sky television. We have weather satellites. We have ultraviolet measurements and infrared measurements, which are changing our understanding of our planet. I want to show you a couple of examples of this. Here we have a volcanic plume. This is in visible light, but in infrared, we actually see where the ash cloud is in a completely different place. So Earth observation satellites are helping us not just understand the planet, but understand in ways that will directly influence us how we are changing this. And in infrared, I want to show you this animation. This is a composite image from 1993 to 2004 of satellite infrared measurements of the oceans of planet Earth. We see the beautiful currents that are there. This is not just a beautiful picture. This is essential to understand the dynamics of the atmosphere, what is happening with climate change. And if we are to understand what we are doing to the environment, getting data from space is essential. But I am not here to talk about Earth observation today. You have an excellent workshop on Earth observation. I want to take this further. Is there a way that science from space could help prevent another mass extinction of life? The answer is yes. And of course, we need to understand the phenomena of comets. Now, we have three very different images of comets here. Comets have been seen throughout human history, around the world. This is a famous scene from English history, 1066, the Battle of Hastings, when William of Normandy conquered England. And if we look at this 1,000-year-old document, we have Harold and his supporters looking at the sky, and they are terrified, because what we see in a corner is probably the most famous comet of all. It's a representation of Halley's Comet, which made an appearance in 1065, 1066. And they are terrified because all over the world, comets have always been regarded as harbingers of death and destruction and bad luck. If you saw a comet, you were not going to have a good day. Now, all of this was superstition and speculation. What do we actually see with a comet? Well, we see an object that looks like a star, only it's not. It's got a sort of fuzziness around it that we call a coma. And the heart of a comet is this part, the nucleus. And night after night, when you see a comet, it moves against the background stars slightly, and the comet coma may develop to form a tail. And once every 20 or 30 years, we have a spectacular comet with a spectacular tail. This is Comet McNaught that was seen from Australia in 2007, and the tail was absolutely beautiful here. However, even more recently than that, in your Soho workshop, you may have seen the story of this comet, Comet Lovejoy, from Christmas last year, that came very close to the sun, so close that nobody expected it to survive its passage around the back of the sun. These are images from the Soho coronagraph, but it did survive. These are the images as it emerged from the back of the sun, taken from Solar Dynamics Observer. And because it survived this for a few days at Christmas, it became a spectacular comet from the southern hemisphere. Two of my favorite photographs. This is from the European Southern Observatory at Paranal in the Atacama Desert. But here you have the comet as seen from the International Space Station. Dan Burbank took this photograph during his 6-month mission on station. And he said, we can see the air glow of the atmosphere. In his 3 missions, this was the most beautiful sight he had ever seen in all of his missions. So comets are spectacular. But if we want to understand comets, we need to understand 2 key areas from physical sciences: gravity and also spectroscopy. And our first activities are going to help us to model gravity much better with our students. Could I ask you to gather around the central tables, please? Now, some of you may have been wondering, why are we coming to ESTEC to learn all about physics of comets with hula hoops, bulldog clips, and lycra? Well, you will be surprised, I hope, when you see how powerful these are for teaching about fundamental physics associated with gravity. We are going to be working in 3 groups of about 5 or 6, and what I want to do is give you a number of activities to explore using these. These are what I call gravity wells. Many of you will have seen in science centres when they have models of these, and we can roll marbles or roll coins. They are usually using them to show how mass influences space-time. So for teaching Einstein's theories, we are not doing that. We are going to be using this to model gravity in a potential energy model. And I will explain for the non-physicists how this works. Before I do this, I need 1 table group who do not mind being volunteers so I can show how to use this. So if I ask people who were on this table, okay, if I could ask you to come around here and arrange yourselves around this gravity well, and if you can all make sure that you see these. Okay, the first thing, sir, if I can ask you to come around to where I am here. The first thing with these gravity wells is we need to make sure the lycra is tight. So when you get your gravity well, if you can just sort of tighten it up until it is quite tight. So, And because the hula hoops are hula hoops, and they're quite old, we need to try and sort of circularize them. Okay, so now we have our gravity well. Now, we are going to be using this for potential energy. And the way this works, we need to hold it all the time horizontally. As you start doing your marbles stuff, this may start to go like this, or it may start to go like this. It's important to keep it horizontal. So I would say if we hold it down at about this level, this will actually work better. When it's up here, it tends to go like this. So we'll hold it sort of this level. Now, first of all, what are we showing? Well, this is now a potential energy zero surface. Now, if you are not used to potential energy, this is an area of space where there is no gravity field. So empty space, no stars or anything. And if a planet comes along and there is no force acting on it, from Newton's laws, it will just move in a straight line at a constant velocity. And we see that. It moves there, it moves here, it moves like this. Of course, there is a little bit of friction, and it is not perfect, but it is a nice way to start. However, if we have a star or a planet creating a gravity field, what it is doing is it is reducing the potential energy. And so what we are doing for a potential energy model is we are using this for the physicists. This is a 1/r potential energy model. But if you are not a physicist, think of this as a gravity well. And as we get closer and closer here, it is getting deeper and deeper. And what you will see is that this, as an analog, will show very clearly some of the real phenomena that we have in orbits. Now, if I now put my marble in, I have a beautiful orbit going around my star, and we can see that it is not circular, but it is actually elliptical. I will want you looking at what happens when you have a slightly elliptical orbit, maybe squash circle, a very elliptical orbit. You will start to see how the velocity depends upon the distance from the source. You will start to see, for the physicists, is t squared proportional to r cubed? You can see so many different things. I will want you exploring this yourselves. For the physicists, though, extra challenge. If I have a single mass here, and this is a potential energy model, at a certain point, what property of the surface will give me the gravitational field strength? Because physicists always think about force fields and potential energies. They are two ways of looking at the same idea. Other things we can do. We can have a single star. We can have a binary star system where we have two masses like this. Okay? You can try to set your orbits up here. Look at what happens when the marble's getting close. We see this in the real solar system. One thing for health and safety with students. I always have students wearing goggles because in our modeling, gravity is an attractive force, but if you let go of this, not only have you destroyed lots of mass, but you've also suddenly having marbles flying everywhere. Also, do not make the marbles, when you start, do not do this, whoosh, because then we will have a hyperbolic escape trajectory out of the solar system with marbles all over the high bay in ESTEC. So go slowly, first of all. Lots of things to experiment with. Think about how you can use this with your students, but I'm hoping you will see that this is not simplistic. You can build very sophisticated understanding with this. So we can try all sorts of things. If I have my potential energy surface, is there a property of the surface that will tell me how strong the gravity field is? It's the slope. So from a potential energy model, if I'm a physicist and thinking this is a 1/r potential, and if I pull down here, the slope, the gradient, if this is 1/r, will be -1/r squared. I'm differentiating it. And that is the nature of the force modeling. So potential energies and force modeling is fundamentally linked. The force is the spatial gradient of the potential energy model. And I'm sorry if I'm losing people in mathematics, but it just shows this is powerful. I've used it with students, pre-university, first-year undergrad students as well, to help visualize the vector calculus of what's happening. But it's also lots of fun. And what I hope you saw is that for comet orbits, very, very elliptical, very, very high eccentricity, squashed ellipses, the planet's orbits are nearly circular. Not quite, but nearly circular. But for a cometary orbit, and we have 3 of them here, when a comet is a long way from the sun, it's moving incredibly slowly. As it comes in towards the sun, its velocity vector will increase and increase at an increasing rate. For Halley's Comet, 76 years to go around the sun, it takes only a few years to do half of its orbit, and then it takes more than 70 years to do the remaining half of its orbit. And we see that with our gravity wells. There are all sorts of other ideas that we can use for the mathematicians. We can use the potential energy modeling. We can talk about gravity wells. So I have included some modeling there of gravity wells in the solar system. And we can even take it as far as classical mechanics, first year undergraduate level. But I also want to now look at chemistry, because if we want to understand the nucleus, the science of spectroscopy is absolutely wonderful. Spectroscopy is used in a similar way to the way that detectives will use fingerprinting. If you have fingerprints, you match against the fingerprints in your database. And this is what we do with chemical spectroscopy. Now, some of you may have used a lot of spectroscopy with students. I want to show you the fundamentals and then a very cheap but effective way of building spectroscopes for all of your students to use. So once again, if I can ask you to gather around the middle table. You know, I think it is wonderful that because every element in the periodic table has its own unique pattern of electron energy levels. When we have transitions, we will get unique frequencies, and hence, of course, we get the spectra that we see. And when we look at the spectra there, which can be obtained in the laboratory, of course, if we map the spectra we see in a distant star with the spectra I see for neon, then I know that neon is present, so chemical fingerprinting. Now, I have 8 of these, so in groups of 2 or 3, we can share these. I don't know how many people have seen these direct vision spectroscopes. How many of you have seen these or have these at school? Okay. Now these, the way that you use these will give a really nice spectrum. The way that you use these is, this part is the part that you look through, the eyepiece, and you aim this at what you want to see. So if I'm looking at the spectra from the lights above, I look up and I see a beautiful spectrum, and I see a number of clear emission lines, so I can match up what is in those lamps. And if you want to, you can probably put a mobile phone and take a photograph there and you have your spectrum. The problem with these, so I'll ask you to test these are 60 euros each. And I know that my school could not afford to have a class set of these. So very often spectroscopy is done as a demonstration activity. However, well, I will let you look at these first so that you can think, I wish my students could use this sort of thing, before I show you the cheap and effective alternative. So if I give a spectroscope to 2 or 3 of you each, so if you come forwards and grab a spectroscope, but sort yourselves into groups, just take them out and remember, just have a look at the lights above. They're very easy to use because you just look in that direction, direct vision. How can our students actually see this phenomena themselves rather than have it as a demonstration? Well, it is very, very easy. I want to show you a spectroscope that is almost as effective. This is a cardboard box, well, a plastic box spectroscope. There are lots of these on the internet. I have tested lots of them, and this one, as a design, I found is one of the best ones. Now, this is only 3 or 4 euros, but I have got an equivalent design as a cardboard template in the resources. So if you can have a CD and you can cut out the cardboard, you can have one of these. The way that this works is we do not have a diffraction grating, but we have a reflection grating. This is using interference from compact disc or a DVD or a Blu-ray to do the interference that we need. And so we make our box. The box slots in, the DVD slots in like this, so that the reflective side faces the window here. And the way that this is used is the light that you want to analyze comes in through the top, and you look here, just like a periscope. So you're not looking like that, you're looking here. You know, with periscopes and students, they all look up, just looking straight. So if I want to see the spectrum of the light here, I just hold this vertically. I may need to tilt it slightly, and suddenly I see the bright spectral lines exactly as I saw here. Now, perhaps I am making this up. Well, you can test for yourselves. Could you see the emission lines quite clearly there? They're coming through. So this sort of spectroscope is very simple, very effective. We have the lights a long way from here, up here. When you are doing spectroscopy at school, when you have the source here, there's nothing else to look at. You put your head there, they see the spectral lines. And for flame tests, we see the lines very clearly in different positions. So it's a really nice introduction to spectroscopy, but in an active way for our students. So I have done flame tests with, where I've not told them what the substance is, but I've given them the spectral fingerprint, and they have to match sodium and lithium and barium, all using these spectroscopes. Very, very simple. What I want to look at now is what has spectroscopy told us about comets? Well, before I do that, I want you to look at the spectrum that is on the screen there. Now, with spectroscopy, we can get bright lines or we can get dark lines. Do not worry. What is important is the position of the lines. Now, here we have 15,000 lines. What do you think this is the spectrum of? Because there are lots of elements there, and all the lines are added together. This is like hundreds of fingerprints all on top of each other. This is actually the spectrum of the sun. It's called the Fraunhofer lines on the solar spectrum. And yes, with your spectroscopes, you will be able to see some of these Fraunhofer lines. Even with if you use a Blu-ray in your box spectroscopes, you'll be able to see these. With a CD, you won't, because a Blu-ray has the lines closer together. It's better resolution. But the beauty of this is that the element helium, the second most common element in the universe, was discovered in the sun by spectroscopy 50 years before it was known to exist on Earth. So I love the story of the element helium. They thought they were looking at the element sodium, but they had discovered an unknown element, the second most common in the universe. Well, when spectroscopy was done with comets, the results were very surprising, because if we look at these species here on the screen, we have carbon dioxide. C2H4 is ethene, am I correct? We've got hydrogen peroxide. We have all sorts of compounds that we find here on Earth. And so when spectroscopy was done with comets, people began to realize perhaps we can build an analog, a model, a representation of a real comet nucleus in the laboratory. And that is what we're going to do for the next demonstration. I have a full instruction kit for doing this in your resources, and I have filmed one of my colleagues doing this. This is a spectacular demonstration that gets the pupils very excited, but we can build so much of our physics, chemistry, and biology from it. So if I could ask you to gather round, please. Before you do this, a couple of words of warning. This can get messy. So I have my white lab coat, which I'm going to wear and live up to the stereotypes. And I should point out that we are making an analog. So I'm not using all of the ingredients, because actually there are thousands of separate molecular species we've discovered in comets. I'm putting in some of the key ones. This idea was first put together by an astronomer called Fred Whipple in the 1930s. And it's called the dirty snowball model, and you will see why. You need a plastic bowl, and you need a black bin liner. And this is a very important part. You need to check there are no holes in it, which I did not check last time, and there were holes. So that is intact. Okay, so this is where I'm going to build my comet analog nucleus. The first thing spectroscopically is that comets are very rich in water if we look on the right-hand side. And so I'm going to put some water into my bowl. In fact, we find that in the outer solar system, you know, many of the moons of the giant planets are made predominantly of water. It is so cold that the water behaves like rock. So we have comets being rich in water. The next surprise, comets were very rich in carbon in its elemental form. So element number 6, carbon powder. This is the last comet I am making today, so I'm going to put it all in. Comets were also found to be very rich in silicates, so I have some sand. Now, some of this, I am cheating slightly. I'm including the spectroscopic discoveries with the direct sampling of material from the Stardust mission. But comet nuclei have them in, so I'm putting in some sand. When we look at the species that we have, CH3OH, C2H5OH, I have members of the alcohol family, methanol, ethanol, propanol, butanol. Well, I have some ethanol here. Well, actually, it's red wine. I thought about using vodka, but that's not setting a sophisticated example, so I'm going to put some red wine in. And I need to give this a good stir. Now, this is the part that many of the students find unbelievable. We have found spectroscopically and through the evidence from Stardust, sampling emission, we have found the building blocks of proteins, the amino acids we find on Earth, we have found spectroscopically in comets. I believe there are maybe 20 or 22 amino acids on Earth from a biological perspective. We discovered them in comets. So the ingredients that make Liam Perrin's Worcester sauce amino acids so flavorful, we also find here. This is going to be a smelly demonstration. But for the last piece of magic, we have the other ingredient. Now, this is where I'm actually going to put on my gloves. The reason being that in this box, I have, I'll put these gloves on, carbon dioxide. But it's carbon dioxide below a temperature of minus 78 centigrade, because on Earth, at atmospheric pressure, carbon dioxide is not a gas, it changes directly into a solid. This is what you are producing as a waste product. This is carbon dioxide as a solid at minus 78 degrees centigrade. And most of the time, comets are way out in the far solar system, temperatures are even lower than this. So we're going to be adding this dry ice to the comet. One thing I must point out, when we do this part, there is the spectacular Harry Potter effect, as you will see. But we need to think that there will be a conflict. The carbon dioxide, the dry ice at minus 78, comes into thermal contact with something at 20 degrees centigrade. It will want to change into a gas and expand hundreds of times in volume. At the same time, the water at room temperature is coming into thermal contact at something at minus 78, will try to form an ice cage to imprison this gas that is trying to escape. We will have a battle. We may have explosive outgassing, so we do need to be careful. So, I will start stirring this. I will take a big wedge of carbon dioxide pellets and I will put them in. So this is where we have the Harry Potter magic. What you are seeing is not carbon dioxide, but it is water vapor condensing from the air. But I'm starting to mix up my chemicals here. You can actually have a feel at the cooling effect there. And we can see that this is a relatively cool, dense gas, which is why I've lost my lid. Please don't tell Shamim. Okay, so I'm pouring the water in. I usually use 2 parts of carbon dioxide to 1 part of water. So I'm going to put in a little bit more dry ice. Now, at the moment, I have the ingredients for my nucleus. But what I need to do is make it bind together. So what I'm going to do now is I'm going to take this out. I'm going to close the bag. You can see why I was wearing my white coat now. We can see the carbon dioxide starting to sublime, changing into a gas. Now, every time you do this, it is slightly different. What I am now doing It is like I am baking bread. I am kneading it, pushing it. I'm trying to get everything to bind together inside. Now, I was using large carbon dioxide granules. The smaller you can get the granules, the better it will work and the quicker because of surface area thermal contact effects. However, this is also where it can get a little bit messy. My apologies to the high bay management team here at ESTEC. Okay. Now, Fred Whipple had theorized this in the 1930s. This is the dirty snowball. This is what he thought a real comet nucleus would look like. And sure enough, yeah, it's hissing and fizzing away. But here I have Fred Whipple's dirty comet snowball. In fact, I have two fragments here. We can see it is incredibly dark because of the high carbon content. It is hissing and it is fizzing away because, of course, we have the explosive outgassing on a miniature scale. This was first theorized 50 years before we sent a spacecraft to rendezvous with a comet. And what we will now see is how accurate Whipple was with this dirty snowball model. This is a genuine comet nucleus analog. What do the real nuclei look like? Can we go back to our places, please? So all of this was theory. In 1986, it was the European Space Agency that finally brought the proof in as to whether Fred Whipple was right or wrong, because a European mission called Giotto was sent to rendezvous with Halley's Comet. It flew to within a few hundred kilometers of the nucleus. Now, I want you to imagine one of these dirty snowballs the size of Amsterdam, because that is what was seen by the Giotto spacecraft. Here we've got the nucleus of Halley's Comet, incredibly dark. We've got explosive outgassing here. In this animation, we can see it is tumbling. And of course, as it got closer to the sun, this material heated up, was ejected from the nucleus, and over time spread out to form a tail, hundreds of thousands and then millions of kilometers long. So in 1986, we had the proof that Fred Whipple was right. The dirty snowball model is what we have with a comet nucleus. But we have other images as well. NASA's Deep Impact Probe in February 2006 not only rendezvoused with the comet, but fired a copper impactor to try and hit the nucleus of the comet. 1/3 of a ton of copper. Now, we knew we would not discover copper in a comet, so we could take out the spectral lines. So what actually happened? Well, this film footage was taken from the impactor as it approached the comet. But that is real time, as that copper impactor got closer and closer and smashed into the surface. And from the mothership, this is the view that was seen, an enormous conversion of kinetic energy into light and heat. But if you have a spectrometer on board, you can analyze that. And this is what we saw. Evidence for water, evidence for carbon dioxide, evidence for organic chemistry, carbon-hydrogen bonds. So I was not just making a school analog here. Everything you saw there has been confirmed, not only on Earth, but from our missions to comets. But if we look at the orbits, we may become worried, because if we see the orbits of the comets and we see the orbits of the planets, they do cross over. And if we want an answer to the question, do we have any evidence that comets or asteroids have actually hit the Earth? I want to show you one of my holiday photographs from 2 years ago. And you will probably be thinking, why has he taken a photograph of a cardboard astronaut with an American flag near a mine shaft? So let's zoom out. There's the astronaut, there's the mine shaft. We can see some hills, so we zoom out. But these are not hills. We are actually inside the most famous meteor impact crater on Earth. This is in Arizona. It's the Barringer crater. It is 1,200 meters wide, 3/4 of a mile. It is 200 meters deep. And this is a view from space. This was created not by a comet, but by an iron-nickel asteroid, so a rocky body, that smashed into Arizona 48,000 years ago. There are fragments of this all over the desert. This has very high density. 9 kilograms per liter is the density, 9 grams per cubic centimeter, or thereabouts. And 92% iron, 7% nickel. Now, this is where we can bring in our high school physics and high school chemistry. Because for the last, since 1945, many countries have detonated nuclear weapons. Now, we can agree with this or we can disagree with this. We have lots of data on how much energy now we need to make a certain size crater in a certain type of rock, because this is what's happened in nuclear tests. And from all of that data, to create a crater like this, in this type of rock, we know how much energy you need, because it's equivalent to 2.5 million tons of chemical explosive. Now, I'm not going to make you do this calculation. There is a very straightforward calculation we can do, but we are here at ESTEC. You have had lots of workshops, and I thought we're not all physicists here. But the calculation that we do, I have the map of this. I do this with my year 9 and year 10 students. If they know how much energy is needed to make the crater, well, we do. It's equivalent to a hydrogen bomb. And if you know how fast the object was moving, well, the computer simulations show it was 13 kilometers a second. From the kinetic energy equation, I can work out the mass of the object. And so these are the steps. I get the students when they're doing mass, density, and volume. Kinetic energy is a half mv squared. They do this modeling, and they work out how big the object was. And the results they get, and I would ask any of you to do this in the evening, the results that you get are surprising. From high school physics, you find the object had the mass of an aircraft carrier, 128,000 tons. But it was so dense that its radius was about half the size of this room. So this was an object, little bigger than this high bay here at ESTEC, that hit the desert with so much kinetic energy, it blasted a crater nearly 1 mile wide. If the object was this big, the crater would have been about this big and this deep. And it's all about kinetic energy. So when we do the cratering experiments, we can bring the mathematics in. It's great for physics and chemistry teaching. I have included an impact simulator that one of my colleagues, Dr. Paul Roche, created in the United Kingdom. I won't show the link now. All I will say is that once you start playing with this, you will never stop. Because what you can do is you can select the size of your asteroid, you can select the velocity, you can have it impact any place you want on the Earth. You can pick a town, you can pick a city, you can pick a country, and it will import it into Google Earth. So you will then have, there's your town, here's your object, this is the angle, and you can actually see the visualization of the crater. So I hope you enjoy playing with this later, but steering your students to use it responsibly. What about in the last 100 years, or in our lifetimes? Do we have evidence of impacts? Well, some of you may have heard of this event, the Tunguska event in Siberia. On the 30th of June, 1908, there was a mystery explosion over the Siberia region. The forests were flattened by the explosion. These pictures were taken in 1927, and they were taken 10 miles, 15 kilometers from the impact site, and the forest had still been flattened. Now, we think this was a comet nucleus that exploded in the atmosphere as it heated up. And if this happened today over the city of Coventry in the United Kingdom, this would flatten every building and every tree for 15 kilometers in each direction. So this was in 1908, a big event. But even more recently than that, I want to show you some film footage that was taken by a tourist in 1972 in a national park in Wyoming in the United States. This is what she saw. A fireball streaking across the sky. And this was also picked up by American radar. It was an object, we still do not know if it was a comet or an asteroid, but it entered the Earth's atmosphere over North America, came within 58 kilometers of the ground, and then skipped out again into space. It lost some of its kinetic energy, but it was moving so fast that it still managed to get away. If it had come 10 kilometers lower, the calculations suggest it would have exploded, and its energy would have been equivalent to the Hiroshima bomb. Now, this was 1972, over North America, with Richard Nixon as president. You can imagine, at the height of the Cold War, how this would have been seen. So we need to be looking. There are objects from space that hit us. In fact, when we look at the Earth, in more than 200 locations, we find geological evidence of huge impact craters. Now, not all of these are visible as Meteor Crater in Arizona. Some of these are very eroded. Some of these we need to use seismology to look at the rock strata. But these are the large ones. And this one here, off Yucatan, the Chicxulub crater, perhaps this is why we are here taking part in this workshop today, because this is the one that is generally accepted as being associated with the extinction of the dinosaurs. And we will look in a few slides, what did that mean for us? Why are we here? How did this tie in with the dinosaur extinction? In 2008, it was one of my colleagues, Kevin Yates, who was the manager of our Near-Earth Object Center. This object was discovered on a Monday night in California. It's automatic telescopes that look, but people look at the data. And this was the first time an object was discovered where we had 100% certainty it was going to hit Earth the next day. And sure enough, the next day, over Sudan, it exploded in the atmosphere. This is a Meteosat image taken from 35,000 kilometers away, looking down on Earth. And we see the fireball here. It was equivalent to 1,000 tons of high chemical explosive. Earth is hit by this sort of object once a month. Most of the time, it occurs over the ocean or it occurs over the desert areas. So we are hit by objects like this. What we need to think about, though, what about much bigger objects, like the one that supposedly killed the dinosaurs? Well, this is a really unusual comet for 3 reasons. It was discovered in 1993. Schumacher-Levy 9, the first reason that was unusual, it's not one nucleus, one dirty snowball, but it's 21 dirty snowballs. And this one here, the G fragment, is 3 kilometers across. I want you to remember that, 3 kilometers, the largest fragment. The second reason it was unusual, when it was discovered, it was not orbiting the sun. Jupiter's gravity had captured it. And the third reason that it was unusual is that 1 year after discovery, it was realized it was going to hit Jupiter on the 16th of July, 1994. So astronomers would have the chance to actually see a comet impact in their lifetimes. Let me show you what happened. This is an infrared image taken from Earth. That is the fireball of the G fragment, 3 kilometers across. These are the scars on Jupiter. This is the scar produced by the G fragment. You can see the size of it there. But just to really show you how big this was, on the next slide, we superimpose this on the Earth. So this is 16th of July, 1994. So in 1994, we had final confirmation that massive events can happen when small objects like comets hit planets. If this had happened to Earth in 1994, this would have caused a mass extinction that perhaps would have wiped out 20% of life on the planet. And that was 1994. Now, before you worry, something like this only hits Earth once every 50 million years or so. But Jupiter does get hit, and an Australian amateur astronomer, not a professional, he took these images that helped prove it. In 2009, he saw a dark spot on Jupiter. He reported this to the professional astronomers. With the Hubble Space Telescope in infrared, we can see it's very hot. This was an impact site on Jupiter. And 1 year later, can you see there? That is a daytime fireball on Jupiter. And his discoveries have shown that Jupiter does help protect the planets in the inner solar system because its gravity is so dominant. We think Jupiter helps shield us from many more impacts. To summarize, though, are comets harbingers of death and destruction, or are they agents of life? Well, perhaps both. Because certainly they have caused mass extinctions. But perhaps if something had not hit Yucatan Peninsula 65 million years ago, if the dinosaurs had kept going, then mammals would never have had the opportunity to be dominant, and we might not be here. On the second point, where did Earth's early water come from? Well, the Herschel Space Telescope has looked at a comet called Comet Hartley 2. And spectroscopically, we see that in the water, the ratio of oxygen isotopes in Hartley 2 is identical to what we have in our oceans. Perhaps that's where our water came from. And finally, did our original chemicals that we need for prebiotic chemistry for life, did they come from comets? These are the big questions, and this is why ESA has sent the Rosetta mission that I think is the most ambitious mission ever proposed by ESA. This was launched in 2004, a 10-year odyssey to rendezvous and land with a comet called Churyumov-Gerasimenko. Now, when we look at the animation, with your gravity wells, do you remember you had the marbles slingshotting around? This is how it got to the comet. Launched from Earth. Then the flybys were Earth, then Mars, then Earth again, then an asteroid called 2857 Steins, then Earth again, then an asteroid called Lutetia. In fact, it was Comet Steins and asteroid Lutetia. 6 gravity flybys, and then for 3 years the spacecraft has gone into deep hibernation. Its temperature dropping until it will rendezvous in 2014 and try and land on the nucleus of the comet. And the last demonstration I want to show around the middle is a physics demonstration of some of the challenges that we have that are linked into the curriculum. So if I could ask you to gather around. Now, if we are looking at the trajectory there, we can see that for 3 years, Rosetta will be effectively shut down. It'll go into deep hibernation. And it's getting further and further from the sun. Now, at some stage, we will have to wake the spacecraft up to switch on the electric systems. But if I have electronic components, metals, if I drop their temperature, what happens to their electrical resistance? If the temperature gets lower, the electrical resistance will also go down. And this means that when we switch Rosetta back on, we need to be very careful because it'll be so easy to overload all of the systems, and then 10 years of mission will be finished. Literally when you switch the spacecraft on or when you wake it up. So we have a demonstration of low temperature resistance, but it's a very unusual one. Now what I have in here is liquid nitrogen. This is nitrogen that has been cooled to minus 196 degrees centigrade, 77 Kelvin. So we can have all sorts of fun with liquid nitrogen, but I am not going to inflate balloons and so on. I want to do the electrical resistance thing. But if any of you want to see what it looks like, I will just tip out a small amount in here. Okay, so this is liquid nitrogen, and I can just have a very small amount I can put on the table, just a tiny amount. And we can see it was running over here. I'm only using a small amount there because I don't want to get it all over the floor in the high bay area. So this is liquid nitrogen. It is magical stuff. But, well, it's not magic, It's science. What are we going to do? Well, I'm not going to be pouring more liquid nitrogen on the table. Instead, I would like to introduce you to my copper tube here. And the physics teachers will recognize this demonstration. First of all, what I have is I have a copper tube. Do not worry that it has a window here. We can see what's happening. This is not important. We can just use any copper tube for this. And what I also have are two small objects. Now, I always forget which one is which. One of these is non-magnetic and one of these is magnetic. That's the magnet, okay? Now, we know that in a gravity field, all masses will accelerate equally. So if I move my liquid nitrogen here, all I'm going to do is to drop my non-magnet through this copper pipe. Okay? And we can see, as it falls through, it comes through very quickly. So here, okay, do you want to put your hand underneath to catch? You can be my catcher today. Okay. It rattled. It's okay. It rattled a little bit, but it took maybe 1 second, half a second to go through. However, I'm now going to take my magnet. Now, copper is non-magnetic, okay? This does not stick. But as a magnet falls, look at the difference. Now, you must catch this one. Now, according to Newton, if gravity was the only force acting, this should accelerate at the same rate. But watch at the difference. Do you see how long it took? Let me show you again. I drop it in the top. Can you see it took much longer to go through? Now, this is just at normal temperature. The reason for that is that when I have got a magnet that moves relative to a metal, it will induce an electric current in the metal. That electric current will create a magnetic field. We have Lenz's law, minus d phi by dt, it will oppose the change and so on. But what has that got to do with Rosetta? Well, let me show you one last time. This is surprising, but if we drop it through, it's still only taking 5 seconds to go through. What I'm now going to do is I'm going to put my tube into the liquid nitrogen. I'm going to let the temperature of this drop. And I'm going to put it in there for about 1 minute. While I'm doing that, when Rosetta arrives, rendezvous with the nucleus of Comet Churyumov-Gerasimenko, it will go into orbit around the nucleus. It will then deploy a lander called Philae that will try to rendezvous with, not really land on it, but more rendezvous with and clamp onto. And then it's got the most sophisticated suite of spectrometers and direct sampling material. It is trying to understand what is the nature of the organic material, the carbon material, and the nature of water on comets. It will change our understanding about comets forever. And I am stalling for time. That still needs a bit more time to cool down. Now, what I'm going to do is when I take the tube out, the only difference with the tube now is it will be much, much colder, which means its electrical resistance will be less. And you'll see the difference. Now, this is much, much colder. Let's see if there is a difference in the time it takes to go through. Did you notice that was a lot longer? Okay. Now, if I left this in for a little bit more time, which I may do, the longest it's taken was nearly 30 seconds to come through. And the students are holding it and they're thinking, this is strange, where has it gone? But of course, this is a fundamental principle that ties in with our understanding of physics, our understanding of electric motors, our understanding of the sun's interaction with the Earth's magnetic field, our understanding of Mars and how it changed. And in this case, it is essential if we wake Rosetta up and we get 10 years worth of mission results. And so I hope you can see we've got another very unusual application here. Liquid nitrogen In the United Kingdom, many universities will supply this to schools. I do not know about other countries, but I would suggest you contact your local physics department at your local university. If you have one researcher who is supportive, they generally can bring liquid nitrogen into schools. Okay. And for the last summary, if I could ask you to go back to your places, please, you will need a pen and a piece of paper. I would just like to conclude with some final thoughts. Very often, and these are my personal thoughts, we are all here today because, we love space. Space inspires us, it's motivated us. And many of my students in the past have said, even the students who are very good at science, have said, what new discoveries can be made? Many of them have the idea that all of the exciting discoveries have already been made. So I just want to show you a few discoveries that have happened in my lifetime that I used to think were impossible. The first one involves the planet Saturn. Now, when I was a child in 1973, I was given a book on astronomy and I fell in love with it. But in 1973, this was the best image we had of Saturn. In 1973, it was the only planet known to have rings. Uranus's rings were discovered in 1977. It was the only planet that looked like this, and at that time, we thought it had 9 or maybe 10 moons. And we knew that one of those moons, Titan, was about the size of Mercury. In my lifetime, we have discovered that Titan has got a thick nitrogen atmosphere. We've sent a European spacecraft not only to Titan, but into the atmosphere and down to the surface. And on a world at minus 180 degrees centigrade, we have got rivers and lakes and shorelines. We have images like this. These are not rivers and lakes of water. It's rivers and lakes of methane and ethane. This is an alien landscape, but we've discovered this in my lifetime in our solar system. My students are amazed whenever I show this photograph, and as long as they've been born after 2006, they were in this picture. You are all in this picture. This is Earth seen from the surface of Mars. And this is a perspective that we could not have had before the space age. But the final task for you is to do with the Hubble Space Telescope. Now, we all know the story of Hubble. Everyone has their own favorite Hubble images. These are some of my second favorite images. This one. I think it is the Lagoon Nebula, about 7,000 light years from Earth, where new stars are being created, being formed. We've got the Cat's Eye Nebula, NGC 6543, where a star has puffed out to form a planetary nebula at the end of its life. And we have galaxies. This is the Whirlpool Galaxy, M51. This is the Sombrero Hat Galaxy, M104. Collections of billions of stars. But before I show you my favorite picture, this is what I would like you to do. And you all must do it, otherwise I will not release you for lunch. What I want you to do is to take a pen and on your thumbnail, draw a small square, 1 millimeter by 1 millimeter, like this. I want everyone to do this for me, please. What I would like you to do, please, is look at your thumbnail. I would like you to now for the mathematics, you need to have an arm that is 1 meter long. So I would like you all to stretch your thumbnail out like this. So this is roughly 1 meter. Look at the size of your thumbnail, and I want everyone to point their thumbs towards the screen. Now, look at the size of the square. That square, when it is 1 meter from your eye, has a certain, what we call, angular size. And that is the size of sky that the Hubble Space Telescope looked at when it took the image I'm going to show you. It was a part of the sky in the constellation Fornax. So this is the scrap of sky that Hubble looked at. This is my favorite Hubble image of all time. And you may think, what is so exciting here? All we have is 10,000 dots. But let's look at these dots here. Each of these dots is a galaxy. And that was in a tiny scrap of sky like this. But what is more amazing, that is incredible, but we can use high school physics to work out the number of stars in the universe. And you can do this by, well, I will not tell you how you do this. I will let you think about this. For the physics teachers, think about surface areas of imaginary spheres. I have done this with my year 10 students. I will let you think about it over lunch. But when they work out the number of stars from this image, it is huge. It is this number here. 1.2 times 10 to the 22. And students can prove themselves that it is more than all of the grains of sand on all the beaches of planet Earth, just from that one image and from high school physics and high school mathematics. But what I find even more amazing, if I think of all the grains on all the beaches of planet Earth, there are more stars, but in that water container, there are more water molecules in that container than there are stars in the universe, because we think about Avogadro's number, 6 times 10 to the 23. So we have an incredible story that mathematics is telling us. And my final thought for you is this. These were the first words that were spoken on the surface of the moon by the Apollo 15 commander, David Scott. And I'll invite you to read it. It is this part that I think is very appropriate today, because I do not think he was talking about space exploration. I think he was talking about scientific exploration. And humanity has only got to where it is. Our society is based on technology. The technology depends upon science. And unless we have that next generation of scientists and engineers, we will not progress further. And that's why it's been such a privilege to talk to you today, because you are on the front line. It is down to you to help make this happen. It's a big responsibility, but I really respect you for pushing forwards in this area. So thank you very much. I will let you look at the meteorites over lunch, and I will let you have a closer look at liquid nitrogen. I have to use it up today. It's been an absolute pleasure and a privilege. Thank you.